Now let's do a couple of examples when we're testing for a population mean. Again, we're going to be using the t-table, so make sure you have that handy. Here are the steps and what goes into each one. So state your null and alternative hypotheses. Because we're testing a mean, our parameter is mu. We have two-tailed, left-tailed, right-tailed. Here's our conditions. We need a representative sample. And then one of the following have to apply. The population must be normally distributed, or our sample size needs to be at least 30. If both of those fail, you'll be provided with a QQ plot and box plot. Here's our test statistic. When we calculate this, make sure you put parentheses around the numerator and the denominator. Just like we saw before, degrees of freedom is n-1. P-values and critical values will be found using the t-table this time. We'll talk more about that next. The decision rules, nothing has changed. Still the same decision rule. And your conclusions are still the same, except now we're talking about means. So there is or is not sufficient evidence to conclude whatever the alternative says about the mean of the population. So before we get into our first full example, let's talk about the table a little bit more. The t-table is set up a little different than the z-table. So for confidence intervals, we use the degrees of freedom and the confidence level. Well, now we're going to use the degrees of freedom and these numbers up here at the one-tailed and two-tailed areas. So these are your alpha values. So we're going to practice doing this in a second, but you're going to match your alpha value and your DF. If it's a left or right-tailed, you're looking at the one-tailed column, the one-tailed row. If it's a two-tailed test, you'll look at the two-tailed row, and you'll match it with your degrees of freedom, and your critical value is inside. Now the caveat to that is everything here is positive. So if you have a left-tailed test, you need to make sure and put the negative sign on your critical value. If it's a two-tailed test, you need to make sure and put the plus and the minus on your critical values. When we get into p-values, it's going to be a little bit different, and so I'll explain that when we get to the first full example. Right now, let's look at example 12, and we're going to find these critical values. So we're told we have 15 degrees of freedom, a right-tailed test. So right-tailed, DF equals 15, alpha equals 0.1. So remember, for proportions, we needed the tailedness and the level of significance. With the t-table, we now need the addition of the degrees of freedom. So our critical value we call T star. So a right-tailed test is a one-tailed test. DF is 15 and alpha is 0.1. So be very careful you're writing 0.10, not 0.01. They're very easy to confuse. And so the critical value is 1.341. Because this is a right-tailed test, that's it. But if we changed things up just a little bit and said our DF is the same, our alpha is the same, but now we're looking at a left-tailed test, you're going to look up this same number in the table, but because it's left-tailed, you need to make sure you add on that negative sign. And then lastly, a two-tailed test, 15 degrees of freedom, alpha is 0.1. A two-tailed test moves you to a different row. So two-tailed, alpha is 0.1, 15 degrees of freedom. So now instead of at 1.341, we've moved over to 1.753. So 1.753, but again, it's two-tailed, so we need this as a positive and a negative. This is what we will do for each of our critical values for means. We will have to figure out what our degrees of freedom is, what our alpha is, and what the tailedness of our test is, match it all up in the t-table, and then make sure our signs are appropriate. And these notes are pretty similar to what we saw before. If your degrees of freedom is not in the table, then round to the closest. As our sample size gets larger, the t-table looks more like the z-table. So example 13. According to the CDC, the mean number of cigarettes smoked per day by individuals who are daily smokers is 18.1. Do retired adults who are daily smokers smoke less than the general population of daily smokers? To answer this question, we obtain a random sample of 40 retired adults who are current daily smokers and record the number of cigarettes smoked on a randomly selected date. The data result in a sample mean of 16.8 cigarettes and a standard deviation of 4.7 cigarettes. Is there sufficient evidence using alpha equals 0.10 to conclude that retired adults who are daily smokers smoke less than the general population? A lot of information. So we know we're talking about means. So our hypothesis statements will be in terms of mu. We are told that the mean number smoked per day by individuals who are daily smokers is 18.1. So this is our status quo mean. It's our population mean. It's what we know currently. The question, which is actually up at the top, it's rewritten at the bottom. Do retired adults who are daily smokers smoke less than the general population? We have a random sample of 40. So our sample size is 40. Out of this 40, the mean is 16.8. And the standard deviation is 4.7. And then we're given alpha. So how did I know to call this X bar an S? It says, this one specifically says sample mean, but even if that word wasn't there, this mean and this standard deviation were both associated with this sample of 40 people. If they both came from the sample, then they are both sample statistics. The mean we call X bar, the standard deviation we call S. So let's state our hypotheses. Again, we're talking about mu. We said the status quo value is 18.1, and our null statement is always equal to. And as we mentioned, the question asks us if we can conclude that retired adults who are daily smokers smoke less than the general population. So this would be a left-tailed test. Our conditions, we have a random sample, so we have a representative sample. It doesn't tell us that the population is normally distributed, but our sample size is at least 30. So we're good to go. Our test statistic looks like this. So X bar is 16.8, mu is 18.1, and we're going to divide by 4.7 over the square root of 40. Use your parentheses if you need to. And you should end up with a test statistic of negative 1.749. And here's where things get a little bit different. We need to find a p-value. Well, in order to find a p-value, we need to start at our degrees of freedom. So df is n minus 1, so it's going to be 39. So start at degrees of freedom, which is 39. And we're going to look for the test statistic, which is 1.749. Our test statistic is negative, but the table does not have negative numbers. So ignore the negative sign for now. "39 degrees of freedom." If you need to use a piece of paper to help guide you, please do so. Okay, we're looking for 1.749. So 1.6 and then to 2. So we know our test statistic is going to fall between these two values. So what we do now is we move to the top of the page and is this a one-tailed or two-tailed test? Since it's a left-tailed, it's a one-tailed test, so we stop right here. And our p-value is going to be between these two numbers. So there's two ways you can write this. You can flip those numbers and write them smallest to largest. So it says our p-value is between 0.025 and 0.05. Or if you don't like flipping those numbers, you don't have to. You just have to flip your sign. Okay, so our p-value is given as a range because we can't find an exact p-value using that table. Exact p-values have to be found using technology. Some calculators can do it. Excel can do it, and the Excel document explains how to do that. There are other computer programs that will allow you to find exact p-values. So let me reiterate what we did. We started at our degrees of freedom and we looked for our positive test statistic. We noticed that 1.749 fell between 1.685 and 2.023. So then we moved up to the one-tailed column. The one-tailed row to find the p-value bounds. This is what we are limited to using the t-table. We are limited to giving a p-value as a range. We can still make decisions. The question is the p-value less than or equal to alpha? Well, our p-value is somewhere in this range, and we know that alpha was 0.1. So if my p-value is smaller than 0.05, I know that 0.05 is smaller than 0.1. So the answer is yes. My p-value is below alpha. I can still reject the null. So state your conclusion. There is sufficient evidence to conclude that retired adults who are daily smokers smoke less than the general population of daily smokers. All right, and lastly, let's find our critical value and make a decision. So previously, we needed to know the tailedness and alpha. And because we're at the t-table, we also need our degrees of freedom. So let's match our df with our one-tailed alpha of 0.1. And when you match these up, 39 degrees of freedom, the value is 1.304. But remember, this is a left-tailed test, so we need to make that negative. Left-tailed tests, everything functions in the left tail. Right-tailed tests, everything functions in the right-tailed. And two-tailed, you're going to have things on both sides. And as before, we plot the critical value first, we shade, and then we plot the test statistic, negative 1.749 is beyond negative 1.304. So as we decided with p-values, we will reject the null. Let's do one more. The fun size of a Snickers bar is supposed to weigh 20 grams. Because the punishment for selling candy bars that weigh less than 20 grams is so severe, the manufacturer calibrates the machine so the mean weight is 20.1. The quality control engineer at M&M Mars is concerned that the machine that manufactures the candy is miscalibrated. She obtains a random sample of 11 candy bars, weighs them, and obtains the data below. Should the machine be shut down and calibrated? Shutting down the plant is very expensive, so she decides to conduct the test using alpha equals 0.01 as our level of significance. Before we even start, I'm going to let you know that the first sentence and a half is unnecessary. It's an explanation or a definition as to why we set the machine at 20.1. We could have started the problem here. The manufacturer calibrates the machine so the mean weight is 20.1 grams. This is our status quo mean. Then it says we took a random sample of 11 candy bars. That's our sample size. And we're given alpha. So we really weren't given a lot of information in terms of numbers, but you were given the data over here. So we'll be able to work with that shortly. First, we can set up our null and alternative hypotheses. So mu equals 20.1. And then the question is, what goes in the alternative? Remember, this first sentence and a half is unimportant to us. So really, what does the question ask? The question says, should the machine be shut down and calibrated? Well, the only reason to recalibrate the machine is because it's off. That does not mean it's off in the less than direction. It means it's off, period. So this is actually a two-tailed test. We can check our conditions. We have a random sample, which means our sample will be representative of the population. And then we have a series of things here. We do not have information about the population weight of these candy bars. So it doesn't say anything about the population being normal. Our sample size is 11, which is less than 30. That's a problem. But you were provided with a QQ plot and a box plot. And so the QQ plot looks normal, right? It follows the line, everything looks good. And the and the box plot, we don't have any outliers. So our conditions are met. If this information was not provided, if we did not have the QQ plot and box plot, and all we had was a random sample of 11, we would need to say proceed with caution because our sample size is not large enough. Part 3 is calculate your test statistic. Well, our test statistic, looks like this. And we're missing information. All we have is mu and n. But we do have this information here. And we can use this to find x bar and s. So remember, x bar is just the sample mean. Add them all up, divide by the total. And then s, it'd be good practice to go through this. S is the one where we set it up as a table. So x, all your data, x minus x bar, and then you squared those values, and then you had to add them up, divide, and take the square root. So I highly suggest you pause this and work through that to make sure you still understand how to do those things. And when you're ready, return. So x bar is 20.3, s is 0.64. So we can complete the test statistic. Again, parentheses. And our test statistic is 1.036. So when we find our p-value, we start at our degrees of freedom, look for the test statistic. Our degrees of freedom is 10. We're looking for 1.036. And this is a two-tailed test. So our p-value is between 0.2 and 0.4. So is our p-value less than alpha? The answer is no. So we finally fail to reject the null. And when we state our conclusion, the only thing that changes is now we say there is not sufficient evidence to conclude. And tell me what the alternative says. The alternative says the Snickers mean weight differs from 20.1 grams. So to answer the question, the machine should not be shut down. So finding our critical value, we need to know we have a two-tailed test and alpha equals 0.01. And again, because it's the t-table, we need our degrees of freedom. A two-tailed test where alpha is 0.01, 10 degrees of freedom, 3.169. Don't forget your signs. Since it's two-tailed, this needs to be plus and minus. Shade to the outside, shade to the outside. And our test statistic is 1.036, which is not in the shaded region. So we fail to reject the null. There are a number of problems left. 1, 2, 3 problems left, and they are mixed, similar to what you did with confidence intervals. So you need to determine means or proportions, and then go through these problems and answer all the questions. So what's your test statistic? What are your critical values? If you would like to draw a picture, do that. Make a decision, state your conclusion. Example 15 reintroduces confidence intervals. So if you need to go back and look up that formula, do so. But each of these asks you the questions along the way. So work through those. Solutions will be posted.